Okay, so maybe we skip this one, number 17, right? It's the same question. So, okay, let's look at number 26. Find an equation relating A, B, and C so that the linear system, I start recording this. Find an equation relating A, B, and C so that the linear system is consistent for any values of A, B, and C that satisfy that equation. Okay, so we're trying to find when is this system consistent? When does it have solutions, right? Consistent means having solutions. So let me write the coefficient matrix 1, 2, minus 3. So let's find some spot here. 1, 2, one, 2, minus 3, and then what? 2, 3, 3, 2, 3, 3, and finally 5, 9, minus 6, 5, 9, 5, 9, minus 6. Is it? Yeah. And we have ABC here. And A, B, and C. Okay, so again, we will use row echelon form, right? So if we do it, we have to eliminate second and so these entries, right? So we have to eliminate these two entries, this one and this one. To do that, I multiply the first row by minus 2 and add it to the second row and write it instead of second row, and minus 5 R1 plus R3 to R3. Okay, so if we do these two operations, what do we get? We get 1, 2, so the first row doesn't change, 1, 2, minus 3, and A. This becomes 0, this becomes minus 1, and this becomes 9. This becomes B minus 2A. What about this one? This is 0. This is minus 1. This is minus 15 plus 15. 15, and this becomes also 9. And this is C minus 5A. Let me know if I make any mistakes here, okay? So now we have the first leading one, okay? So this is my first leading one. Let me use my highlighter. So this is my first leading one, and this will be my second leading one. So, and I can also eliminate the third row, right? So let's first eliminate the third row. Or so if we do this operation minus row 2 plus row 3 to row 3, and then what do we get? We get 1, 2 minus 3A, and 0 minus 1, 9, B minus 2A, and this will become 0, 0, 0, and this will become C minus 5A, and this will become plus D minus, no, minus D plus 2A, right? Okay, this is the final thing that we get. Of course, we can multiply the second row by minus 1, but that won't change the result. So this system will be consistent if and only if this part This thing here is 0. So this must be 0. Right? So what is the condition then? So this becomes C minus 3A plus B must be 0. So this is the condition for the system to be consistent. Okay, so if this is not 0, then the system has no solutions. So that's the answer. Any questions? No? Okay, so this is also a similar problem, right? I think we did this, right? Yes, we did this one. So let's, okay, so finding the inverse matrix. Let's look at number 19. So find all values of A for which the inverse exists. What is A inverse? So when does the inverse exist? The inverse exists, so in this section we don't know determinant, but we can use it now. So inverse exists if and only if the determinant of the matrix is non-zero. Okay, so if it's 0, then the inverse does not exist. If it's not 0, then the inverse exists. So if it, how can we compute the determinant of the matrix? There are several ways of doing this. One way is expanding it in a row or column. For example, we can take the third column here. So if we expand this matrix determined in the third column, then we get only one term here. So this is minus 1 to the power 3 plus 3. The coefficient is A. And if I delete row 3 and column 3, I get this 2 by 2 matrix. So this matrix becomes A, and determinant becomes A, and this one is minus 1, right? So we want this to be non-zero. This means A shouldn't be 0. So if A is 0, then this matrix does not have an inverse. If A is non-zero, this matrix has an inverse. So how do you find the inverse matrix? Let's remember that. So what do? We write the matrix, right? There was another way in the third chapter. So we write this, then we write identity matrix 1, 0, 0, 0, 1, 0, and 0, 0, 1. Then what we do is we use elementary row operations to have identity on the left-hand side. So we want this side to be identity and this part to be A inverse. So how does it work? Okay, so we can start by swapping these two rows, right? If I swap these two rows, I get the first row of the identity. So if we do this, row 1, if we row swap row 1 and row 2, what do we get? Let's look. We get 1, 0, 0, then 1, 1, 0, then 1, 2, 8, and I have to repeat the same thing on the right hand side. So if I swap row 1 and row 2, I will get 0, 1, 0, and 1, 0, 0, and 0, 0, 1. Okay, that's the first operation. Now I have to make these guys equal to 0. And to do that, I use these row operations, minus row 1 plus row 2 to row 2, and minus row 1 plus row 3 to row 3. So what do we get if we use those things? So let me copy it. So let me copy the whole thing. Okay, so if I use these row operations, this will become 0, and this will become 0. And none of the other things will change, and this will become minus 1, right? And this will become minus 1. Okay, so that's the first step. Then what do we do? We want to make this guy equal to 0. So to do that, I have to multiply first the second row by minus 2 and add it to the third row. So let me copy it again. So this will become, this entry will become 0, right? Good. What about here? So this will become minus 2. And I multiply minus 1 by minus 2, so it will be 2. 2 minus 1 is 1. So I get this. And what is the final thing? Now, the final thing is we divide third row by 8. So I divide third row by 8. And you see from this operation that A must be different than 0, right? So we found that A should be non-zero, and we have seen it in our operations as well. So A should be non-zero. So if A is non-zero, I can divide by A, and I will get. So let me copy it here. So this becomes 1. This becomes minus 2 over 8, and this becomes 1 over 8, and becomes 1 over 8. Okay, so this matrix on the right is the inverse. And this matrix is the identity. So if you remember, we said that if we can carry out this operation, then the matrix is invertible, and what we obtain on the right is the inverse matrix. If we cannot carry this operation, then the matrix has no inverse. Okay. So in this case, the inverse matrix is given by this this part. Okay. This part is the inverse. Any questions? Okay. Okay. Uh, let me do another inverse matrix example. This time, let's use this Adjugate matrix method. Okay, Adjugate matrix. So you remember there was something called the Adjugate matrix. So how was it defined? So it was defined as the uh, the transpose of these cofactors, right? A 3, 2, a 3, 3. So we have to take the transpose of this matrix. This is for 3 by 3 and for other cases as well. So we're trying to find the inverse of this guy using this Adjugate matrix. So what was the cofactors? What was, for example, let me first copy this so that you can see it. Oops. Okay, so what is A11? What is A11? A11 is the first entry, which is 1, times, so the position of this guy, which is 1 plus 1, times the determinant of the matrix obtained by erasing this row, this column, and this row. Okay, so if you do that, you get 1, 0, 1, 1. So what is this guy? This is basically 1, right? A11 is 1. And you see A12, so these guys, this cofactor will be 0, A12 is 0. A12 is 0 because I will multiply it by 0. What is A13? A13 is, it will be again minus 1 to the power 1 plus 3. And if I erase those rows and columns, I get 1, 1, 1, 0, 1, which is again 1. Okay. And I carry on these operations. So let's do it for second row. So A21 is 1 times minus 1 to the power 1 plus 2. And what do we get? We get 0, 1, 1, 1, right? So this determinant will be, so this will be minus 1 times minus 1. This will be plus 1. A22 is, what is A22? It's again 1 times minus 1 to the power 2 plus 2. 1, 1, 0, 1. This is again 1. So I'm suspecting that all of these guys are 1. No, A23, I'm sorry, A23 is 0. Okay, let's do for the last row. So what is A31? A31, you see it's just 0 because the corresponding entry is 0. This guy is 0. And A32 is 1 times minus 1 to the power 3 plus 2, which becomes 1, 1, 1, 0, 1, 1, 1, 1, 0, which gives us what? 1, right? So last one is A33. This is again 1 times minus 1 to the power 3 plus 2, 3 plus 3, and this time it will be 1, 0, 1, 1. So all the cofactors are 1. So it was interesting. So we found the Adjugate matrix. What is the Adjugate matrix? So let's write it. So where should we write it? Let's write it here. So what is the Adjugate matrix? Adjugate matrix is so it will be 1, 0, 1, 1, 0, 1, and then second row is 1, 1, 0, 1, 1, 0, and the third guy is 0, 1, 1. So it's basically the same as the matrix A, but there's also a transpose here. So this matrix is special. Its Adjugate matrix is a transpose of itself. Now, what is the inverse matrix? So if you remember the formula for the inverse matrix was basically 1 over determinant times this Adjugate matrix. Okay. So we have to compute the determinant for this one. What is the determinant of this matrix? Let's see. So to compute determinant, we can use cofactors of any row or any column. So let's use the rows of the first, first row. So this is basically hold on a second. Okay, guys, I made a mistake, but it won't change the problem. So my mistake was this. So when we computing the cofactors, I did something wrong. We're not basically multiplying with the entries of the matrix. Okay, so there shouldn't be ones here. So since all of these were one, we were lucky, and the result will not change. So this guy is also not multiplied by 1. Okay. So I'm sorry about that. So nothing is changing here. So it's the same thing. But the important thing is when we're computing the cofactors, we don't multiply with the entries of the matrices. Okay. Adjugate yanlış mı yazdınız? Yanlış yazmadınız mı? Yanlış mı yazdık? 1, 0, 1, 1, 1, 0, 0, 1, 1. Yok. Doğru. Bunun transpozu ama. Transpozunu alacağız. Okay, so when we computing the determinant, what we do is we can compute this one, A11 times A11 plus A12 plus A13 times A13. Okay, so now like small a's are the entries of the matrix and the capital A's are the cofactors. Okay, so when we're doing this, so A11 is 1, so this is basically A11 plus A13, right? Which is 1 plus 1, which is 2. So the inverse matrix becomes what? The inverse matrix becomes this guy divided by 2. So all the entries are divided by 2. So let's write it. Now first I take the transpose of it, so it will become 1 over 2, 0, 1 over 2. The second row becomes second column, 1 over 2, 1 over 2, and 0. And the third row becomes 0, 1 over 2, and 1 over 2. Okay, this is the inverse of the matrix. Any questions? Okay, sorry about that mistake, but it's good to make mistakes so that we can learn better, I think. Okay, so let's look at this guy, number 3. Let be the matrix obtained from A after the operations. If determinant B is 2, find determinant of A. So how do we do this one? Let's see. Now, in the first step, okay, so we're using row operations, right? So I'm multiplying the third row of A by 2. So if I do this operation on A, I get a new matrix, right? So this is this matrix is the matrix A, but its third row is multiplied by 2. In this case, we know that this is 2 times determinant of the matrix A. Okay. So if I do this operation, the determinant is multiplied by 2. What about this operation? If I do this operation, the determinant will be multiplied by -1. So okay, so let's say that this is our new matrix B. So now what am I doing? I'm using this operation on the matrix B. So I'm swapping the row 1 and row 2 of B, and this will be same as minus determinant of B. Okay. What about these operations? Now, if you remember, these operations do not change the determinant, right? These two operations will not change the determinant. So they will have the same determinant as this matrix. So at the end, what do we get? At the end, we get a matrix. So if we have like 1, 2, 3, 4 operations, at the end we will get a matrix. Let's call that matrix. So I think I used the wrong name. So B is the final result here. So this should be matrix, for example, C. Okay. Let's give this name also C. And this one also C. So what we get at the end is determinant of the matrix B is the same as this matrix, determinant of the matrix when these two rows are swapped. So what we get is this is equals, we said that this equals minus determinant C. And we know that determinant C is 2 times determinant A. So this will become 2 times determinant A. So what is the final result? So we know that the determinant of B is 2. So determinant of A is basically -1. Any questions? Evet, bugün kalemim pek güzel yazmıyor arkadaşlar. Kalemin bayağı ucu kopmuş, o yüzden yazmakta çok zorluk çekiyorum, görüyorsunuz. Kusura bakmayın o yüzden. Yeni kalem sipariş ettim ama gelir mi bilmiyorum. Umarım yarınki derse kadar gelmiş olur diye düşünüyorum. Sorusu olan var mı? Okay, let's do this number 4. I don't think we have enough space here. Let's copy it. Where should I copy it? So let's copy it here. Okay, so we will solve this determinant. We want to find the determinant of this matrix. I cannot erase that. So by converting this matrix into triangular form, okay? So we will bring this matrix into like an upper triangular matrix. So we want to make these entries 0. Okay, so to make that, what we do is, okay, let's start by this operation. These two operations. So if you do that, what do we get? So both of these operations do not change the determinant, right? This one doesn't change the determinant. This one doesn't change the determinant. So determinant of A is the same as this determinant. 1, 2, 1, 0, 0, 1, 2, 3, and this guy becomes 2. No, this guy becomes 0, 0 and 4 and 1 and minus 1. What about this one? This becomes 0. This becomes minus 6, minus 3 and minus 1. So this is the same determinant. So in this next step, I will make these two entries 0. This one and this one should become 0. To do that, what are my operations? Again, let me write my operations. So minus 4 times second row added to the third row goes to the third row, and plus 6 times the second row plus the fourth row goes to the fourth row. After these operations, what do I get? I get 1. So this becomes 2, 1. This becomes, okay, let me write first these entries. This is 0, minus 8, minus 7, minus 12, minus 13, right? I think it's right. So this becomes 0, 12, minus 3 is 9. And what about this one? 18 minus 18 minus what? 17. Is this right? Robuşta mı yanlışlık yaptık? Bir saniye. Eksi 4 ile çarptım 0, eksi 7 oldu. Eksi 4 ile çarptım eksi 12, eksi 13. Burada mı yanlışlık yaptık? Nerede yanlışlık yaptık ya? Burada mı? Okay, let me check it. 0, 4, 1, minus 1. This is true. İlk aşamada. Burada mı yanlışlık yaptık? Row 3. Row 3. 2 ile çarptım 0. 2 ile çarptım 4. 2 ile çarptım 2 eksi 1 artı 1. 2 ile çarptım eksi 1. Bana doğru gibi geldi. Tugay Sarıcı. Sen değerleri yanlış yazmışsın. Tamam. Sorun yok. Okay. So what do we do? Okay, guys. Help me. So we divide the third line by minus 7, right? minus 7, what happens? I'm dividing row 3 by minus 7 and writing this instead of row 3. So in this case, how does the determinant change? So this is basically minus 7 times this determinant. 1, 2, 1, 0, 0, 1, 2, 3, and this becomes 0, 0, 1. What is this guy? 13 over 7, 0, 0, 9, 17. This is the result. Okay, so if I, and the final operation is minus 9 times row 3 plus row 4 to row 4. What happens here? So this doesn't change the determinant, so our final answer will be this one. 1, 2, 1, 0, and this is 0, 3, 13 over 7, and what about this one? So 17 minus 9 times 13 over 7, right? Okay, I think we are finished, so let's look at it. Now, how do we compute the determinant of a triangular matrix? So when we're computing the determinant, we basically multiply the entries on the diagonal, right? So these are the entries on the diagonal. The product of the entries on the diagonal, so which means this is minus 7 times 1 times 1 times 1 times 17 minus 9 times 13 over 7. Or I can write this as 9 times 13 minus 7 times 17. So whatever this number is, that's the result of the determinant. Any questions? Yanlışlık yapmadık değil mi arkadaşlar? Bir bakın. Okay, I think it's true. Okay, so we did one example about this, so we don't need to do this. So as a final thing, let's remember this Cramers rule. Okay, so Cramers rule was a rule to compute the solution. So let's see how it works. So we have a formula for Cramers rule, number 8. Number 8. Let's see how it works. So how do we write the solution? So we have the formula was like this. X1 is determinant of. So what we do here is maybe I don't write determinant. I just write that in this symbol. So instead of the first column of the matrix, I replace it with the vector b. So this becomes 1 minus 1 and 4. So then this becomes 4, 2, 0, and 2, 2, 1. And I divide this to the determinant of the matrix A. Okay. So what about the other columns? What about the other components of the solution? So for x2, I replace the second column of the matrix A with this vector 1, -1, and 4, and 2, 2, and 1. And for x3, I do it, I replace the third column, right? So, no, yeah, 3, 1, 3, 1, 3, and 4, 2, 0, 1, -1, and 4, divided by the determinant of the matrix A. You see, we need to compute the determinant of A only once, and once we find it, we can divide it by all of these. We can find out, like, we can use it for all these x's. So if we compute this, we get solution. Okay, I don't know if I should do it or not. I think you can do this, right? So we did the examples about this one. So the final thing you have to write in the vector form, x1, x2, and x3, like this. Any questions here? So I don't want to compute all these determinants because you see my stylus pen is broken, so it's very difficult to write. It's very frustrating for me. So yeah, let's see if we skipped any good questions. Compute the determinant by, so we did this one. We don't need to do this one again, right? We did one question about it. Okay. So okay, let's look at these ones. Which of the following homogeneous systems have a non-trivial solution? Okay, so let's discuss about this one. So these are homogeneous systems, and we want to find when do they have non-trivial solution. What do you think about it? If determinant is 0, then there is non-trivial solution. You're right. So if determinant is 0, so if you compute the determinant, so for example, for this one, determinant is 0, right? Because the rows are not independent; they are dependent. Okay, this one will have non-trivial solution because we can eliminate one of these rows. So this one has non-trivial solutions. So non-trivial solution means it will have infinitely many solutions. So how many independent solutions can we find for this one? How many independent solutions? What do you think? There are infinitely many solutions, but how many independent solutions are there? Basically, what I'm asking is find the basis. So find the dimension of the solution space of this system. There are not infinitely many independent solutions. Okay, so for this one, there can be at most 3 independent solutions, 1 or 2. 1 or 2. So if you remember, So if you remember the discussion at the beginning, so the rank of the system is what? Rank of the system is number of independent rows. So there are only two independent rows here. First one and the second one are independent. So rank is 2. Rank of this system is 2, which gives us the nullity, right? Nullity must be 1. Nullity is number of independent vectors, independent solutions. So we can find at most one independent solution. Okay, the other ones will all depend on. So this solution space will look like something like this: an arbitrary vector times a fixed vector. All the solutions will be in this form. If it was 2, all the solutions should be written in this form. So if it was 2, but it's not 2, okay, for this one it's just 1. What about the let's look at the second one, okay? So does this system have non-trivial solutions? So first of all, the first and the second row are independent, right? One is not a multiple of the second one. So the question is whether we can obtain the third row by using first row and second row. If we can, then this system will have non-trivial solutions. If we can't, then no. So can we obtain the third row by using the first and the third? Or another way of looking is just look at the determinant, right? So if you look at the determinant, what is the determinant of this system? So if this determinant is non-zero, then there is only trivial solution. If it is 0, if the determinant is 0, then there will be infinitely many solutions. Okay, so can anybody see if we can obtain the third row from the first two ones? So if I multiply the first row by -1 and second row by -1, no, it doesn't make, right? 2y, 2, no, it doesn't make. So it looks like these three rows are independent. So this determinant is in fact not 0. Okay, you can check whether it's 0 or not. I think it's non-zero, and since it's not 0, then this system has only trivial solution for part B. Doesn't have a non-trivial solution. What about part C? So again, it's easier to check the determinant than trying to see whether there are independent rows or independent columns or not. Okay. So remember the fundamental theorem of when we discuss fundamental theorem of linear algebra and the rank and things like that, the number of independent rows and the number of independent columns are equal. That's an interesting result. So if there are, so if these rows are independent, it means these columns should also be like independent. So number must be same. So it doesn't change whether you look at the rows or columns. Okay, it's I think it's interesting. Okay, so I will finish the class here. Tomorrow, I think I will solve some problems about chapter 4. Okay. Okay, let's finish here. See you tomorrow. I hope my stylus will come. Thank you for coming. See you tomorrow.